Hey, welcome back. Today we're going to be talking about how to solve angular velocity and angular acceleration problems with calculus. So this is for AP Physics C mechanics students or for students of similar classes. So first of all, there is a concept that we've been talking about lately. So this omega represents angular speed or angular velocity. It looks like a W. And what it is a change in the angle, the angular displacement, so to speak, divided by time. So delta theta over delta t. And it turns out that we can use that as a derivative of d theta over dt to get the instantaneous angular speed or angular velocity. This is very much like saying velocity is equal to dx over dt. It's just the rotational version of it. And similarly, this is like saying acceleration is dv over dt, where instead of talking about linear or translational units and variables, we're talking about rotational variables here. So that's what we're saying, is that angular acceleration is the derivative of omega with respect to time. So angular speed or angular velocity with respect to time. So in the animations here, you can see a constant angular speed with this first animation. And with the second animation here, you can see an angular acceleration, just to think about the concepts that we're talking about here. Lastly, if you see the term rigid, I just want to point out that this is used in AP Physics C problems. And when it says rigid, one way to think about this is that there are different points as the object rotates. Like if this is the axis of rotation right here, they are all in reference to each other, maintaining their shape, and they can move in different directions, right? All of the points are moving in slightly different directions, with the exception of if you're talking about something along the radius as it rotates, then they're all moving in the same direction. They just have different tangential speeds. But that's a quick rundown of what we mean by rigid objects. Let's go ahead and talk through a couple other things. So the first thing to talk about is, of course, you can graph this just like you could graph a position versus time graph. You can graph a theta versus time graph. And we can think of this as the slope, right? The slope at any given point, the instantaneous slope at any given point, or value for t, you can solve for that omega value. And if we were to plot this, for this scenario right here, I want you to think about what would we see if we were to graph omega versus time. So what does this delta theta graph show, this theta versus time graph show for a type of angular speed that we would see? Well, what we would see would be something like this over here. Omega versus time is just constant for this scenario. And so if you're going to go from this to this, you can do that with taking a derivative or differentiating a function. Now, if we're going to go backwards, let's say we have a function over here, or we can do a geometric thing where we solve for the area of a rectangle or multiple areas and do some simple math to be able to solve for that. Then you can work backwards and solve for the angular displacement in terms of radians. So remember that when you take a integral, you end up with the change in values for the other variable that you end up with. Okay, and similarly, let's take a look at another way of thinking about this. If we graphed omega versus time, like we have right here, then you can say, well, our acceleration is just going to be the instantaneous slope at any given point. That's the derivative. And so if we were going to plot this, what do you think you would expect to see? In a very similar way, we would see something like this. And again, if we were going to work backwards, you could do so using integration of a function if you have a function, or integration in the sense of the area under the curve if you had geometric shapes under the curve, so to speak. Alright, there are two problems that I want to go over with you really quickly. And the first is here. If you want to pause, go for it. The scenario is over here, and then I want you to think to yourself, which is going to be the correct scenario. And I'll summarize this really quickly. So it says the bar here is pivoted about one end, here's the end, and it falls and makes an angle theta with the vertical at any given time. Which of these graphs represents the bar's angular velocity omega as a function of time? So pause for a moment if you choose and think about what the correct answer is going to be. And so how to reason through the answer here. the rod is definitely going to be accelerating as it goes down, so its angular speed will be parabolic in some sense, or at least part of the parabola, so clearly that's not going to be A or B. I do want you to think about whether it's going to be C or D. It's definitely not going to be C though, because it's not coming to a stop. It's not like this was thrown upwards and it's coming to a stop. So it's definitely not C. The question is whether or not it's D or E. And I could see people getting this wrong. It is a little tricky. Here, the correct answer is E. And that is a little tricky because we normally consider clockwise rotation to be considered to be negative. Now, how you could justify that is, they don't make it terribly clear, but this is an implied zero. If that were the case, then you could, I guess, assume that this is 0, but in a positive. If that's 0 right here, then I guess you could assume that this is some positive value and it becomes more and more negative as time goes on. But it's not starting out with a positive rotation at all. But it's not being thrown backwards. Again, D would more represent, assuming this is 0 right here, that it has some positive rotation initially and that it eventually comes to a stop, assuming this is 0. So that's how we can justify this is going to be our correct answer for E. Another really important thing to note here, as the rod comes down, it gets more and more horizontal, the torque is actually going to be greater. That's a really crucial idea. If you think about the center of mass of the rod right here, the farther it gets over here, the center of mass here is a greater torque because the force due to gravity is more perpendicular to the center of mass for the rod as it rotates down. As opposed to like right here, the force due to gravity is pulling down right here and the torque isn't as great. It's a really crucial idea. Let's apply that idea to another problem here. So if you want to pause for a moment and think about what the answer is going to be here, please do so. Go for it. I understand it's tempting to think about a flat acceleration. If this object were just dropping, if it were not rotating, then a flat acceleration would make sense. If we're talking about a linear or a translational acceleration, like just an object that's dropped. Here it's a little more difficult in difference because remember, that center of mass as it rotates, it comes down here and it's, over time, it's getting farther and farther away from this axis of rotation, which means you're going to have a greater torque, and torque is proportional to the angular acceleration that's going to be experienced. So it's going to be maximized right when it hits this horizontal position right here, which means that you would start with no angular acceleration effectively, and then you would end up with a maximal angular acceleration over here. So this is the only one that actually makes sense. But it's based on this idea that torque will increase as the center of mass moves farther and farther out as this thing comes down. Center of mass moves farther and farther out from the axis of rotation, leading to a greater and greater angular acceleration that's maximized at the horizontal position here. I do want to say also, as we compare D and E, notice that D is concave down, E is concave up. D is more correct in terms of describing reality because if you think about as this rod falls down, the majority of the distance of the center of mass as it moves from the axis of rotation out is at the beginning part of the falling process. As it gets closer to being horizontally oriented, then it's got less and less motion in the x-axis of the center of mass, so to speak. So it would make more sense to say that this is a concave down acceleration, angular acceleration, as opposed to a concave up like we see in E. So that's how you would reason through this. I've done screencasts on an entire year of physics as well as most of the ideas for our AP Physics E mechanics. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.